Um, good morning, ladies and gentlemen. I still cannot believe that I'm here and presenting the Nobel lectures. So first of all, I'd like to give sincere thanks to the Royal Swedish Academy of Science. Today, I'd like to present two topics. One is the growth of gallium nitride on the Sapphire substrate, and the second is the p-type gallium nitride. Majority of my presentation overlaps that of the previous presenter, Professor Isamu Akasaki, but I'd like to explain these achievements from the young researcher's point of view. So at the end of my presentation, I'd like to send a message to the young generation. First, I'd like to give the example how blue LEDs changes our lives. For young generations, maybe most familiar items would be portable games, and also the cellular phones or the smartphones. The first portable games were commercialized in 1976, and the first cellular phones were available in 1989. But until 1990s, at the end of 1990s, all the displays are monochrome. So the young generations, I'd like to emphasize that you can enjoy the full color displays by the emergence of the blue LEDs. Okay. This is the very famous view graph showing the improvement of the performance of the LEDs. This was written by Dr. Heitz, the retired US scientist. In 1962, US Professor Nick Hornyak invented and developed the commercially available red LEDs using the gallium arsenide phosphide. And since then, the performance of LEDs improved by a factor of 20 per decade. So this improvement is called the Heitz law, which is similar to the Moore's law in case of silicon-based LSI. And since after the red LEDs, yellow LEDs and green LEDs have been also commercialized. And as for the blue LEDs, in 1971, Professor Jack Pankow developed the gallium nitride-based LEDs, but it was MIS-type LEDs, so it was not commercialized. I started the nitride research at 1982. After the 14 years of the research and experiments, Professor Akasaki moved from the company to the Nagoya University in 1981, and I joined his group in 1982 as an undergraduate student. The reason why I choose his laboratory is because the radiation research subject, nitride-based blue LEDs, are so simple and so fascinating. At that time, I thought that the size of the TV system based on brown tube was so bulky. So if I could achieve blue LEDs, I could change the world by shrinking the size of the displays. At that time, I was not aware that this subject was so difficult. I thought it was, maybe it's easy. The reason why, I'd like to explain why it was so difficult to grow gallium nitride If you want to grow large size bulk gallium nitride, you need a high pressure and high temperature, which is similar to the synthesis of the diamond, or even higher. So you need to use chemical reaction to reduce the pressure and the temperature. In addition, you need foreign substrate for the epitaxial growth of gallium nitride. But the ammonia, the nitrogen source, is so reactive at high temperature. So the candidate of the substitute material is very, very limited. The sapphire is one of the most promising substrate because it does not react with ammonia so heavily. But the most serious problem of the sapphire was the large lattice mismatch of 16%. In general, the lattice mismatch for the heteroepitaxial growth should be less than 1%. So the 16% lattice mismatch is almost impossible to grow gallium nitride. Professor Pankov developed in 1971 the MIS-type gallium nitride using the hydride vapor phase epitaxy, using the metal gallium, hydrogen chloride, and ammonia. But they could not achieve the P-type gallium nitride, so efficiency is limited to be low. Also, another problem of the difficulty in achieving the bright blue emission was related to the sensitivity of human eye. Responsivity of the blue, pure blue light is only 3% compared with the yellowish green 555 nanometer emission light. So the students tried to start the research of the gallium nitride growth by metal organic vapor phase epitaxy. At that time, the funding situation of the university in Japan in mid-80s is not so sufficient. So the students have to develop the crystal growth reactor by ourselves, headed by Dr. Koide. But that situation is very happy or very good for us because we can manage the configuration by ourselves. I have tried more than 1,500 times by changing the growth conditions such as growth temperature, growth flow rate, liner tube configuration, and the susceptor shape, and so on and so on. But unsuccessful. I could not get high-quality gallium nitride film. For me, the large lattice mismatch was too great to overcome. So almost 2 years passed without success. In February, year 2085, that was almost the final month of my master course. At that time, only one foreign student and I decided to start the PhD program the next April. And while other Japanese students enjoyed the graduation trip, I carried out the very lonely experiments, okay? Dr. Koide 1 year elder students focused on the growth of aluminum gallium nitride, while I focused on the growth of gallium nitride. If we compare the surface morphologies of these two materials, his aluminum gallium nitride seems to be better than my gallium nitride. So I thought that the aluminum containing material or even aluminum nitride is important to improve the surface morphology. So I decided to use the aluminum nitride before the growth of gallium nitride. But I knew that the substrate temperature should be higher than 1200 centigrade for the epitaxial growth of aluminum nitride. But as I mentioned, we used the very old system, old oscillator, so it did not work well, even though I managed to control. And just at the time, I remembered the hint during discussion in the laboratory. Dr. Sawaki, the associate professor, mentioned that in case of boron phosphide on silicon growth, the lattice mismatch of which is as large as 24%, peripheral of phosphorus gas is very effective to improve the surface morphology. And he claimed that phosphorus atoms act as the nucleation center. So I imagined that the low temperature deposition of aluminum nitride and very tiny aluminum nitride should act as the nucleation center. Then I proceeded the gallium nitride growth. So when I took the sample out from the reactor, it was almost the same as the Sapphire substrate, perfectly flat and perfectly transparent. So my first impression was, oh, I forget to supply the gallium sources, trimethyl gallium. But when I checked all the bulbs, I found that I operated properly. So I checked the sample by Nomalsky type optical microscope and found that we achieved the highly flat gallium nitride for the first time. And following the suggestion of Professor Akasaki, I checked the crystalline quality, electrical properties, optical properties, and found that all the properties were superior to the previous reports. So this technology is called the low temperature buffer layer and can be used by many researchers worldwide, like this. Then, of course, our next target is to realize P-type gallium nitride. From 1985 to 1988, I concentrated on growing the zinc-doped gallium nitride, but all the samples shows highly resistive or N-type. When I measured the luminescence, photoluminescence at cryogenic temperature, I observed the very narrow excitonic peak. So I was excited and tried to present at the Japan Society for Applied Physics annual meeting held at Nagoya University. And when I entered the room, I was surprised that only 4 people, including Professor Akasaki, chairman, I, were in the room. At that time, majority of the researchers were interested in the zinc selenide or zinc sulfide. the researchers of the nitrides are quite minority. Also, I observed this phenomena that during the cathode luminescence measurement of zinc-doped gallium nitride, the blue luminescence was irreversibly enhanced. So I call it the low-energy electron beam irradiation, the Levy treatment for short. But even after the Levy treatment, the zinc-doped gallium nitride did not show the p-type conduction. In 1989, I became the research associate of the Professor Akasaki's lab, Nagano University. And when I read the book, The Bonds and Bands in Semiconductor, written by J.C. Phillips, I saw this graph very, very appealing. This graph clearly shows that in case of gallium phosphide, magnesium is much, much better than zinc in terms of the activation of acceptor. As for the magnesium, I should comment that Professor Maruska, at that time, the Stanford University student, developed the world's first violet but MIS type LEDs using the magnesium-doped gallium nitride. Okay. Dr. Kito at that time, master course student, and I grew plenty of magnesium-doped gallium nitride. The as-grown magnesium-doped gallium nitride shows highly resistive, but after the Levy treatment, Dr. Kito said that some sample showed p-type behavior. But I knew that by hot probe measurement, I knew that the hot probe measurement is not so reliable. So even though we presented, maybe no one can believe the p-type conduction. So he measured the Hall effect measurement, and finally we recognized that we have achieved the p-type gallium nitride for the first time. In 1992, Professor Nakamura claimed that he can realize the p-type gallium nitride even by a much simpler method, that is thermal annealing, in 1992. Okay, the mechanism is shown here. The as-grown sample was, the magnesium was passivated by hydrogen. So the Levy treatment or the thermal annealing is effective to dissolve the hydrogen from the passivated magnesium, okay. Which was first explained by Professor van Besten in 1992. Okay, we are still have the problems of blue emission. The band gap of gallium nitride is in the UV region. For the blue emission, we need to grow the indium-containing alloys, indium gallium nitride. Of course, we have tried to grow the indium gallium nitride, but it is also very, very difficult. So we grew indium gallium nitride with the indium content less than 3%, which is, the band gap is still in the UV region. In 1989, Dr. Matsuoka NTT succeeded in growing the blue luminescence indium gallium nitride by growing it at very, very high ammonia flow rate condition and also in nitrogen carrier gas atmosphere. So combining the high-quality crystal technology, P-type gallium nitride technology, and the double fatal structure of indium gallium nitride and gallium nitride, Professor Nakamura's team first succeeded the commercialization of nitride-based blue LEDs in 1993. And also, his group realized the quantum well-based structure in 1995, which is also very important for the improvement of the efficiency of LEDs. Maybe he will explain in the next presentation. Okay, let me explain how the indium gallium nitride LEDs contribute to the energy savings. Maybe you remember that the great earthquake attacked East Japan in year 2011. Before 2011, nuclear power plant supplied the 30% of the total electricity generation in Japan. But now, none of the 48 reactors were operated now. Every reactor was not operated. So we have to find the solution for adapting these 30% electricity. Some research company in Japan predicted that by year 2020, more than 70% of the lighting is replaced to LED lightings, by which we can save about 7% of the total energy consumption by year 2020. More importantly, by combining the LED lightings with solar cells and batteries, we can supply the very simple lighting system, especially to the young generation or children who cannot be access to the electricity. So we can supply the lighting so children can read the book or study even at night. Okay. This is the message to the young researchers. When we realized the low temperature buffer, I was only 24 years old. And when we realized the P-type gallium nitride, I was 28 years old. Of course, I was very, very lucky that I can carry out the research under the excellent supervision of Professor Isamu Akasaki and the distinguished colleagues. But these days, the facilities and funding should be much, much better than year 2080s. So I'd like to see that the younger generation try and tackle more the more difficult subject for the contribution of the improvement of mankind lifestyle. Okay, I'd like to acknowledge distinguished colleagues, Nagano University, Meiji University, and Nagano University, to the GOSEI, to the Center of Research and Laboratory, UV Craftery and NIXO. And finally, I'd like to acknowledge my family for continuous support. Thank you so much for your kind attention.